On the 26th of December 2004, at 3 minutes to 8 in the morning local time, the seafloor west of northern Sumatra began to break. It kept breaking for at least 10 minutes. That is the longest duration of faulting ever observed. The rupture ran between 1,200 and 1,300 kilometers along the northern section of the Sunda megathrust, the longest fault rupture ever recorded. The magnitude is still refined by researchers today, initially recorded as 8.8, but officially at 9.1, with recent studies favoring 9.2 to 9.3. It is the most powerful earthquake ever recorded in Asia, and the second or third most powerful anywhere since modern seismography began in 1900. Of all the seismic energy released by every earthquake in the 100 years to 2005, roughly 1/8 came from this single event. It made the entire planet vibrate by as much as 10 millimeters. It triggered earthquakes as far away as Alaska, and it lifted the seafloor. That is the part that matters, because an earthquake does not make a tsunami by shaking the water. It makes one by moving the bottom of the ocean vertically. Along parts of the rupture, secondary faults, splay faults, popped narrow strips of seafloor up in seconds, which raised the height and the speed of the waves that followed. The town of Loknaw, on the Sumatran coast nearest that rupture, was destroyed. Across 14 countries, an estimated 227,898 people were killed. It is the deadliest tsunami in recorded history. This episode is about a single question. The wave took hours to cross that ocean, and almost everyone it reached was taken by surprise. Start with the physics, because it explains the failure. In deep water, a tsunami is almost nothing to look at. It can be less than a meter high, spread across hundreds of kilometers of wavelength, moving at the speed of a jet aircraft. A ship at sea can pass over one and never notice. From the air, you would see nothing. That is precisely why detecting a tsunami is hard, and why it needs a network of sensors rather than a lookout. What changes everything is the shore. As the water shallows, the front of the wave slows, the back of it catches up, and all that energy stops traveling forward and starts going upward. On this coast, in places, that meant water 30 meters high. Now the warning. In the Pacific, an ocean where tsunamis are relatively frequent, a warning system had existed for decades, sensors, and a communications network to turn a detection into an evacuation. In the Indian Ocean, in 2004, there was no tsunami warning system at all. Not a weak one. None. The reason is not negligence so much as arithmetic. Tsunamis are rare in the Indian Ocean, even though earthquakes in Indonesia are not. Rare hazards are the hardest ones to fund. A system that might be needed once in a lifetime competes against problems that arrive every year. And so, the earthquake happened, and the information existed. Seismographs worldwide recorded it within minutes, and there was no route from that knowledge to the people on those beaches. Distance was no protection either. Somalia was hit harder than Bangladesh. Kerala, on the far side of India, was struck because tsunami waves diffract around land masses. The word is Japanese. Tsunami, harbor wave. Japan has the longest recorded history of these events of any country, which is why the world uses its word. Which is not a perfect name, because they do not only happen in harbors, but every alternative is worse. The one you have probably heard is tidal wave, and geologists and oceanographers actively discourage it because tides are caused by the gravity of the moon and the sun, and a tsunami has nothing whatsoever to do with either. The term stuck because of what a tsunami looks like when it arrives. Not a breaking wave, but an extraordinarily high, forceful tide that keeps coming in. Scientists once preferred seismic sea wave instead. That is not right either, because earthquakes are only one of the ways to make one. A tsunami is a series of waves caused by the displacement of a large volume of water. Anything that displaces enough water will do it. Earthquakes, volcanic eruptions, underwater explosions, landslides, glaciers calving, meteorite impacts, and rapid changes in atmospheric pressure. The understanding is older than you might expect. In the 5th century before the Common Era, the Greek historian Thucydides suggested in his history of the Peloponnesian War that tsunamis were related to submarine earthquakes. He was right, and then almost nothing happened. Understanding remained slim until the 20th century, and a great deal is still unknown. One of the main open questions is unnervingly basic: why some very large earthquakes make no tsunami at all, while smaller ones make dangerous ones. The events that cross whole oceans have their own name, teletsunamis, and they come from the biggest megathrust earthquakes. Chile in 1960, Alaska in 1964, the Indian Ocean in 2004, Tohoku in 2011. At the other end, an earthquake as small as magnitude 4.2 in Japan can trigger a local tsunami that devastates a stretch of coastline in a few minutes. And then there are the landslides, which produce something else entirely. In the 1950s, it was realized that giant submarine landslides could cause waves far larger than anyone had thought possible, because a huge volume of rock moving fast transfers energy quicker than the water can absorb it. It was confirmed in 1958 in Lituya Bay, Alaska, where a landslide produced the highest wave ever recorded, 524 meters. It did not travel far, it hit land almost immediately. It struck 3 boats anchored in the bay, each with 2 people aboard. 1 rode it out, 2 were sunk, and 2 people died. In 1963, a landslide from Monte Toc slid into the reservoir behind the Bajant Dam in Italy. The wave went over a 260-meter dam by another 250 meters and destroyed several towns. Around 2,000 people died. Read that again. The wave did not break the dam, it went over the top of it by 250 meters and kept going. Scientists gave these waves a name of their own, megatsunamis. Some are much older. Storegga, off Norway, about 8,000 years ago, a sediment failure whose cause is still unknown, possibly overloading, possibly an earthquake, possibly a release of gas hydrates. Others are within living memory, the Grand Banks in 1929 and Papua New Guinea in 1998, both from earthquakes destabilizing sediment. Both dissipated before crossing an ocean. And there is a live scientific argument about whether a collapse of a volcanic island, Cumbre Vieja on La Palma is the usual example, could send a mega tsunami across an entire ocean. Many researchers dispute it. No landslide large enough to cause a transoceanic tsunami has occurred in recorded history, which is a sentence that offers rather less comfort the longer you look at it. But some people did evacuate, not many, and how they knew is the most important thing in this story. On the Indonesian island of Simeulue, close to the epicenter, the islanders felt the shaking and went inland to the hills before the water came. They did it because of folklore. Island stories recounted an earthquake and a tsunami in 1907, and what those stories told you to do was simple. If the ground shakes hard, go up. Oral tradition carried across 4 generations functioning exactly as a warning system is supposed to function. The same thing happened in the Andaman Islands. Anthropologists initially feared the Onge, already a very small population, might have been wiped out entirely. Many of the Andaman tribes evacuated, and casualties among them were lower than expected. Onge folklore describes, in the recorded phrase, huge shaking of ground followed by high wall of water. Almost all of the Onge appear to have survived. On Mai Khao Beach in Phuket, in Thailand, a 10-year-old British tourist named Tilly Smith noticed that the sea had gone out much further than it should have and that the water was frothing and bubbling. She had learned about tsunamis in a geography lesson at school 2 weeks earlier, and she recognized what she was looking at. She told her parents. They told the hotel staff the beach was cleared. Around 100 people were on it. At Kamala Bay, north of Phuket, John Chroston, a biology teacher from Scotland, recognized the same signs and got a busload of holidaymakers and local people onto higher ground. Stop and look at that list. An island's folklore about 1907, an oral tradition among the Onge, a school geography lesson, a biology teacher. In the absence of any instrumented warning system, what saved lives that morning was knowledge, held by ordinary people and acted on within minutes. Which is worth holding on to, because the technical lesson people usually take from this day is about buoys and satellites, and the human lesson is about whether anyone on the beach knows what a receding sea means. The receding sea is worth explaining, because it is the one sign almost anyone can read, and it is not universal. A tsunami is not a single wave. It is a train of them, and whether a coast sees the trough first or the crest first depends on which way the seafloor moved. Where the trough arrives first, the sea withdraws hundreds of meters in minutes, exposing seafloor that is never normally uncovered. That is the free warning, and it lasts only as long as the trough does. Where the crest arrives first, there is no withdrawal at all. The water simply keeps coming in and does not stop. And a tsunami does not break like a surf wave. It arrives as a wall of water that keeps arriving, a sea level that rises and then travels inland as a flood moving at the speed of a car. In Aceh, the province closest to the rupture, the water arrived within about 20 minutes of the shaking. There was no plausible technological warning that could have beaten it. For that coast, the only warning that could ever have worked was the earthquake itself, and the knowledge that a long, violent shake near the sea means leave the shore immediately. That is precisely what the folklore on Simeulue told people to do, and Simeulue is closer to the epicenter than Aceh is. The response was immediate and enormous. Donations exceeded $14 billion, one of the largest humanitarian responses in history. And in January 2005, a United Nations conference in Kobe, Japan, decided to establish an Indian Ocean tsunami warning system. Kobe is a pointed choice of venue. It is a city that was itself devastated by an earthquake 10 years earlier, almost to the day. A tsunami warning system has 2 halves, and they matter equally: a network of sensors to detect the wave, and a communications infrastructure to turn that detection into people moving. The detection half is the easy half. Seafloor pressure sensors can register the passage of a wave less than a meter high in the open ocean and relay it to a surface buoy and up to a satellite. The hard half is the second one. A detection is worthless unless it reaches a person on a beach, in a language they speak, with enough time and enough credibility to make them walk uphill. And systems decay. Indonesia's network fell out of service in 2012. A reminder that infrastructure for rare events is exactly the infrastructure that gets quietly defunded between disasters. Nor is the gap unique. The Caribbean has no comprehensive system of its own and relies on the Pacific Center. There is a hard truth inside all of this. A warning system is a bet placed by one generation on behalf of another, against an event that may not arrive for centuries. The geology has not changed. The Sunda megathrust is where the Indo-Australian plate slides beneath the plates that carry Sumatra and Java, and it is doing so continuously. In 2005, a magnitude 8.6 earthquake struck off Nias, just south of the 2004 rupture. It is not considered an aftershock. It was most likely triggered by the stress the first earthquake transferred along the fault. That is how these faults work. Relieving stress in one place loads the segment next door. A great earthquake is not the end of a sequence, it is often the start of one. The 2004 earthquake is also thought to have triggered activity in volcanoes along the same range in Aceh, and the 2005 event stirred the caldera at Lake Toba. And the earthquake had a foreshock, though nobody could have used it. A 2002 earthquake off Sumatra is now believed to have preceded the main event by more than 2 years. That is the recurring problem with warning. The signal is often there, it is only legible afterwards. There is one more measurement from that day that is difficult to hold in your head. The rupture was long enough that the earthquake could not be described by a single point at all. 1,300 kilometers is roughly the distance from London to Rome or from New York to Florida. That is how much fault moved. And it moved for 10 minutes. Most large earthquakes are over in under a minute. The shaking people feel is the fault finishing its slip. This one kept going long enough that seismologists watched the rupture propagate, which is why the magnitude estimates keep being revised. Instruments in 2004 were not built to size an event that large, and each reanalysis of the long-period data has nudged the number. The Andaman and Nicobar Islands sat directly on the northern end of that rupture. Some of those islands were permanently tilted. One coast lifted clear of the water, the other drowned. On North Sentinel Island, home to the Sentinelese, a people who have consistently refused contact with the outside world, the reef around the island was lifted, and the community appears to have come through. There is a thread here that runs back through this whole series. In Volume 1, we spent an episode on the Cascadia earthquake of 1700, an event with no written record on its own coast, reconstructed from Japanese ledgers, dead cedar trees, and the oral traditions of the people who lived through it. Those traditions were treated, for most of the 20th century, as stories. They turned out to be data. In 2004, on the other side of the world, the same thing happened in real time. On Simeulue and in the Andamans, stories about older waves put people on high ground before the water arrived. A geography lesson did the same job for a 10-year-old on a beach in Thailand. Knowledge is the warning system. Everything else is plumbing. 227,898 people died on the 26th of December 2004 in 14 countries. The earthquake that killed them released about an eighth of a century's worth of the planet's seismic energy in 10 minutes, along a fault that had been quietly locked and loading for hundreds of years. There is now a warning system in that ocean. There are sirens on those coasts, and evacuation signs on those roads, and children in those schools who are taught what a receding sea means, which is the only useful thing a disaster of this size can leave behind, a coastline that has been taught to remember something it did not experience.